Okay, now I'm going to go through a further example of a energy calculation in a contraction, this time with a bump in the middle of the contraction. So go to the spreadsheet, week 2 and 3, we've got the varied flow, specific energy calculations, and the 5th tab. We'll see what the question is here. Well, it's pretty much exactly the same as the last example, the one on the tab before. Uniform flow in a channel, calculate the width, which will cause critical depth, and then if the width is slightly narrower than that critical width you just calculated, what will be the effect. So this time we've got a third part added. If there's a bump of 0.2 meters high in the throat, of the contraction, what difference will this make? So we're going to go back to the calculations. It's going to be pretty much the same as the previous one. We're going to first of all calculate the flow using the Mannings after we've calculated A, P and R for the given width and depth, N and slope. So we've calculated Q. So yeah, probably should be in that colour. I've got a cell here for dz equals 0.2 in yellow. I'm going to put it in 0 here, just so we can check we've got our formulae correct, and we'll change it to 0.2 when we get to do these calculations. I have to first of all calculate these other intermediate, lowercase q1, v1, fr1, 0.45, so it's subcritical. Calculate the y crit at this point. Y crit is below y1, so subcritical. Calculate E. Energy in the flow at this point, 1.6 meters, 65 meters, and energy crit, which is 1.3. So critical energy is below the energy we have, so it's subcritical. Okay. Now we're going to do the calculations for what is the critical width, the width that causes critical flow in the contraction. Now this time the difference in our calculations are that we're going to write down our energy upstream is equal to the energy in the flow at the throat plus a delta Z. So that's a slight difference. We need to encompass this delta Z into our algebra. So it's this panel here which is absolute key to understanding this contraction with a bump in it. We know that at the critical flow we've got critical energy, and we know that critical energy is 3/2 times the critical depth, and it's this critical depth actually we're trying to do a calculation of. We can work out that critical depth with our formula, and actually this allows us to encompass a width in it. So this is the second energy term which we're going to have in our equation here. So we get that energy balance equation and substitute in our E2 crit expression, which is this one. We can do a bit more algebra on that to get a final calculation for the width, which will give us critical flow at the contraction. We've got in here this delta Z term. If you were to look at the spreadsheet prior to this, we'll see that this delta Z term is not here, it's not here. Okay, this is the key. Now back on our calculations here, I'm actually going to put this expression here as a separate calc just to make it a bit clearer. So the equation we put in Excel is not too long, so let's calculate that term, 3/2 E1 minus Z2. So So 2/3 E1 minus Z, 2 times E1 minus the delta Z, which we've got at 0 for now, divided by 3. The critical width is this formula, equals square root of capital Q squared divided by G, C1, divided by that number we just calculated, all cubed, 2.16. Critical depth is our normal critical depth formula. You can have that, Q squared over, lowercase q squared over 2G over G to the third, or capital Q over B, and I'll do that one because it just makes it clearer what we're calculating. So capital Q squared divided by the new B squared divided by G, all to the 1/3. Gives me 1.103. Okay, just flick onto the spreadsheet before. Okay, yeah, so there it is. Here we are, exactly what we had before, but we've got a bump in this. So what do we expect to happen when there's a bump? So we'll increase that bump height to 0.2. So we see B2 crit has increased in width, Y crit has changed. That's how we know it's from 1.13 to 0.2.97. So it's decreased in depth. That's because we've given a bit of potential energy from the bump, so the flow energy is a bit less. Okay, I'm going to change this back, so it's looking about right. Okay. Second part of the calculation says if the width of the contraction is 2 meters, so 2 meters is going to be less again than the critical. What do we get? So critical depth again is going to be equal. So the width, because width is less than critical width, depth is going to be at critical. We can calculate Q2, lowercase q2, based on this new width. So that's going to be equal to capital Q divided by the width. We can calculate YC2, which is just the normal Q squared over G to the third. So the brackets, Q squared over G raised to the 1/3. Okay, 1.16. We're on a DZ, so we should be getting the same answers as last time. If we were to now calculate the critical depth, the upstream depth caused by the change in the width of less than critical, we need to go back and look at our algebra. So that same energy balance, energy at 1 is equal to energy in the flow at 2 plus the height. So we rearrange that because we know that energy at 2 is Y2 crit. We can do our algebra here, and what we get is this cubic again. Again, go through this yourself to check this, but what's different from the previous calculation, and we've got this minus delta Z in the P2 term. That's the change. So we put in our values for the cubic that we're going to have here. A is always 1 in my formulations, B is this formula here, minus delta Z, minus, let's go back, 3 times Y2C, which I've calculated, divided by 2. C is always 0 in my formulations, and D is the Q squared over B squared 2G. Q squared over the width we have, which is B squared over 2 divided by G. And this we calculate from cubic solvers. Um, 1.15, is that what we had before? So, not the same. I think we should have had the same. Here we're using a DZ of 0 at the moment. Minus 1.743471. Looks like that D is slightly not quite right. Q squared over B squared 2G. Right. Yes, the mistake is not that B, because it's B1 squared. Let's get rid of that. B1 is what we were given originally of 3, B1 squared over 2G. And these are some 2 calculations that we got before. So I'm going to say that Y1 is the lower one, Y2 is the bigger one. So the energy at this point we can calculate based on the solution which we say is correct. And I'm going to put that in green. Okay, so this is exactly the same as what we had before. But what happens when we increase the bump from 0 to 0.2? Remember, we got a decrease in the Y critical. And we're reducing the width even further, so we get a 1.863838 upstream. That's the depth has increased from the original depth 1.5. It's gone up 30 centimetres, 34 centimetres, quite a high increase. Look at how this is the solution to that quadratic. Or you can put these formula in to the cubic solution. Let me paste that in. Okay, we see that there's that's where the solutions are here, 0.5 and 0.83 we know. Okay, so increasing the bump increases the height upstream. Well, if it was a 0 bump, it was increased to 1.6 from 1.5 to 1.6. If it was a 0.2 bump, it goes up to 1.8, 1.84. So more than the height of the bump. Let's have a look at what the energy curves look like. Well, I've plotted the energy curves for you from these tables here. Let's just look at the energy curves, what we started with. The first one we started off with upstream is this orange curve, and the two solutions that we're interested in are here. This is the energy data at 2. The blue curve is the energy at the contraction. And remember, we wanted critical depth here, so this is where critical depth is. And this line corresponds to the line of same energy as this dashed yellow line, same energy as this solid yellow line. How can that be? Because these are energy difference. The difference between difference in distance, horizontal distance here, is the delta Z, is the 0.2. Okay, 0.2. So we see the numbers here, 1.654 to 1.454. Okay, so those are the relative things. So that's the orange and the yellow, orange and the blue lines, how they relate to each other. The third part, second part of the question really, was what's the situation upstream. Now this dark blue line is the energy in the flow upstream after you've got a bump of 0.2 and a narrowing of less than the critical, and the narrowing goes to 0.2. Effectively this orange line moves to this blue line, and that's the new energy curve. We can look at the energy points here. The energy point here will be 1.941, and that will correspond to that energy new that we did a calculation of. Okay, so you need to be able to explain all the points on these energy curves and draw them yourselves. Remember that these horizontal lines on my charts here correspond to the critical depths, for the blue line for the orange, the green one for the blue curve, and the brown one for the dark blue curve. Okay, thank you.